Welcome to Geology 105 Environmental Geology. This is Dr. Widanagamage and my office is located 118D Carey Hall in the School of Engineering. Textbook for the class is Introduction to Environmental Geology by Edward Keller. Fifth edition is recommended. However, the Environmental Geology book by James Richard, the third edition, is also recommended. The course is web course and Blackboard enabled. The quizzes, assignments based on the lessons that we cover in the class will be up in the Blackboard. And please make sure to read the syllabus and the emails for more information on the exams, about the chapters and quizzes and assignments. Office hours are online. You can email me anytime if you have any questions, but expect responses within 24 to 48 hours. Please make sure to write your name, student ID, course number in subject line of your email, unless you will not get a response. Why do we study about environmental geology? So everything has a beginning and end. Our Earth began in 4.6 billion years ago when cloud of interstellar gas known as solar nebula collapsed, forming protostars and planetary systems. Life on Earth began little later, like 3.5 billion years ago. Since then, we have diverse animals and plants which are emerged, prospered, died out, leaving fossils to mark their life or the place in the Earth's history. Geology is the science of processes related to the composition, structure, and history of the Earth and its life. When it comes to environmental geology, it is an applied geology. Especially, it is useful for geological information to help us solving conflicts or problems in land use, to minimize environmental degradation and maximize the beneficial results of using our natural and modified environments. Environmental geology will provide opportunity for you to study about earth materials, examples soil, rocks, minerals, how do they form, their potential use as resources or waste disposal sites, and effects of human health, and also give opportunity to study about natural hazards and to study about environmental protection. Oil, gas, coal are the three major resources of energy that we currently use very widely all over the world. Studying environmental geology will make better understanding about these natural resources. Many of today's medications are derived from benzene, and benzene in turn is derived from petroleum. Almost all over-the-counter pain medications such as aspirin are based on this petrochemical. Petroleum-based fibers are durable, readily available, and easy to maintain. So combined with the fact that they are generally cheaper than natural fabrics, synthetic fibers becoming increasingly popular in the world of fashion and home goods. Mining, metals, industrial minerals, gems. These are the three major economically important mining activities today. Inappropriate mining can release acid waste into the groundwater, causing environmental issues. Also, petroleum exfoliation, the removal, transportation, and waste disposal can damage the environment. Acid mine drainage or acid rock drainage referred to the runoff formed of acidic water infrequently comes from the areas where metal mines or coal mines mining activities have exposed rocks containing pyrite, and the result is oxidizing or rusting of certain types of sulfur-bearing minerals. Acid mine drainage is the formation and movement of highly acidic water rich in heavy metals. This acidic water forms through the chemical reaction of surface water, such as rainwater, snowmelt, pond water, and shallow subsurface water with rocks containing sulfur-bearing minerals. resulting in sulfuric acid. Heavy metals can be leached from rocks that come in contact with the acid, a process that may be substantially enhanced by bacterial action. Therefore, it is important to study about these acid mines that are related with these mining activities. Geol 104 is the course that mainly discusses about geological hazards, but Geol 105, the environmental geology, mainly will be discussing about resources. However, we'll be covering the geological hazards as well, such as earthquakes, tsunami, volcanoes, landslides, and floods. Water, air, and soil protection is mainly the environmental protection. Look for the contamination in this illustration. Mixing of gasoline with toxic chemicals. To understand this process and to identify this kind of problem, you need to have the knowledge of environmental geology. You need to know about the porosity and permeability of these rocks and soils. And also you need to figure out a way to determine how to detect the direction of the waste movement, and how far is this from the groundwater, and how long that this takes to mix with the groundwater. So these kind of issues needs to be solved with the knowledge of environmental geology. This is an incident where raining over city landfill. You can see how contaminated water percolate through and mixing with groundwater. To identify this kind of environmental issue, you really need the knowledge of environmental geology. So you can see this orange color plume is moving from one place to other, and that is the toxic material or the unhealthy material that is moving and polluting the groundwater. So these kind of issues we will be talking about, and also the knowledge with environmental geology will help you understanding this kind of situations. To begin, we should talk about the solar system. As any geology class, we should talk about how do we form and how do the earth formed. The nebula theory or protoplanet hypothesis is widely accepted, and people talked about it, people believe about it. So what that means? The Eagle Nebula, with its intensely cold gas and dust, finger-like pillars where new stars are thought to be forming. The formation of solar system, including the Earth and other planets, is still a hypothesis. It's called nebula hypothesis. It explained that the disk of gas and dust swirling with the time at a given at a very high velocity. The rotation moves the denser and heavier materials towards the center of the orbit, while lighter and less dense materials leaving out. The solar system formed about 4.5 billion years ago from a huge swirling cloud of dust. It is within nebula that stars are born. Our star, the sun, or the proto-sun, was created in one such nebula, and it's ignited and gave energy to rest of the planets, including Earth. Telescopes. How do we know that this is the case? So we have to rely on physical constraints, telescopes, meteorites. The Finding Hubble telescope is a big invention in planetary sciences. This allows us to look deep into space to observe the birth of stars similar to our sun and study planetary objects much more closer than earlier. Meteorites are space material. Those provide the evidences for the composition of the original planetary materials. This is a piece of L&D meteorite showing white inclusions. These inclusions are aluminum-rich minerals that formed first in the solar nebula. The inclusions are surrounded by material with lower condensation temperature which aggregates later. LND is in essence preplanetary material. In studying it, scientists can read the history of the beginning of the solar system, and with it, for the first time, scientists had found a key to unlocking the first half billion years of the Earth history. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. These are the planets that we already know about our planetary system. There are two different categories that you can categorize these planets into: terrestrial planets versus Jovian planets. The terrestrial planets in the warmer inner solar system, that's more solid and more dense planets. They are towards the center of the solar system. The Jovian planets are outer in the solar nebula. So they are more gaseous and more giant, more less in density. The Pluto does not fit the category of terrestrial or Jovian planet. It is more like terrestrial but lies far away from the sun and has low density just like Jovian planets. Some astronomers believe that Pluto belongs to the family of comets. Therefore, we do not classify Pluto into either Jovian planets or terrestrial planets. And with that, we are going to look more into the Earth, because Earth is our planet. So the differentiation of the Earth or the layering of the Earth started later after it formed. It's not at the beginning. If you think about the primitive Earth, it's just as similar as the meteorite that you can see today. There's no layers, there's no chemical segregation within the Earth. It was completely just a massive body of the material, of the original material. After protoplanet formed, accumulation of heat from radioactive decay of short-lived elements melted the planet, allowing materials to differentiate into layers based upon the density. If you think about the crust, mantle, core, so based upon the density is increasing from surface to the bottom. So the crust is the lesser in density compared to the core. So crust is around 3 to 70 kilometers, very thin, very thin outer rocky shell of the Earth. The mantle is hot, solid that flows slowly over the time. It's rich in iron and magnesium and silicon. The core has two pieces, two parts: outer core, inner core. So the outer core is metallic liquid, mostly iron. The inner core is metallic solid, mostly iron and nickel. So based on chemical properties, Earth has three layers: crust, mantle, core. However, based on physical properties, Earth has lithosphere, that is the solid, rigid part of the Earth. Is basically the crust and the upper part of the mantle. Together it's called lithosphere. Below that you have asthenosphere, which is soft, flexible, ductile, and that is where you're going to talk about the changes in the physical properties coming from lithosphere to the asthenosphere. Lithosphere is solid, rigid. Asthenosphere is much more weak and soft and more like jelly kind of. It's more plastic rather than the brittle. So asthenosphere is plastic zone on which the lithosphere floats. And outer core, inner core, and the mesosphere. Mesosphere is the lower part of the mantle, and the outer core is liquid, inner core is a solid. So the physical properties are changing in each layer, which differentiate the Earth's layers. So if you ask a question about the Earth's layers based on physical properties, Your answer should be lithosphere, asthenosphere, mesosphere, outer core, inner core. If you ask a question about the Earth's layers based upon the chemical properties, then it's basically crust, mantle, outer core, inner core. What is isostasy? Isostasy is very important concept in geology. So that is the gravitational equilibrium between Earth's lithosphere and the asthenosphere, and in such a way that the tectonic plates float at an elevation which depends on their thickness and the density. Plate tectonics, very important concept in geology. And first of all, what is the driving force for plate tectonics? What drives the plate tectonics? Basically the thermal convection is the driving force for plate tectonics. We talked about that in few seconds. Plate tectonic theory, the originally proposed in late 1960s, included new understanding of the sea floor and explanation of driving force. This describes lithosphere as being broken into plates that are in motion, explains origin and distribution of volcanoes, fault zones and mountain belts. Here is the driving force for plate tectonics, thermal convection. It is very simple. It's very similar to what you're doing in your kitchen when you boil up a chunk, if you boil up your water kettle. It's the same principle. When you heat it up, the water particles get heated up, and it's going to be less in density, so they tend to rise up, and the cold water tend to be more denser compared to the hot water, so the cold water coming back to the bottom. So likewise, this circular path is called the thermal convection. That is the same thing that's happening in the earth. So these convection forces could move this lithosphere on top of the asthenosphere, creating different types of plate boundaries. There are three major plate boundaries: divergent, convergent, transform. Divergent boundary, the plates move apart from each other. The magma rises, cools, and forms new lithosphere, typically expressed as mid-oceanic ridges. The convergent boundary, there are three types of convergent boundaries. It could be continental-continental convergence, it could be continental-oceanic convergence, or it could be oceanic convergence. In this particular example, you're looking at is a continental-oceanic convergence, where the oceanic crust has higher density compared to the continental crust. The oceanic crust is sinking underneath the continental crust. The situation is very similar to Pacific Ring of Fire. The Pacific Ocean is shrinking today. The Pacific plate, oceanic plate, is sinking underneath the North American plate. So this is why you have numerous igneous activities, volcanic activities, and number of earthquakes along the west coast in US. So in this example, plates move towards each other. It creates mountain belts if it's a continental-continental convergent boundary. And volcanoes are very common at these subduction zones. The oceanic plates may sink into the mantle, and it's going to be melting. The mantle melting process creates this series of volcanoes. Transform plate boundary. The plates slide past one another. The fault zones, earthquakes mark boundary. So San Andreas Fault in California is an example for transform plate boundary. And again, one thing to keep in mind, transform plate boundaries are very conservative. There's no construction or destruction of the crust. You can expect more and more earthquakes, but no volcanoes at the transform boundaries because there's no melting of the crust going on like in the subduction zones. Thank you.